Okay, hello and welcome to the mark scheme for the mock exam GCSE Physics 2018. So we'll get right into it. Question 1. Okay, so the question's telling us that a tennis ball is being thrown upwards. There are 3 different positions. We have position A, B and C. Nice easy question to get started. We're given the information. The initial speed down here, V, is 5 meters per second. And we know that we have a mass of 0.058 kilograms. So, part 1, write down the equation that links kinetic energy, mass and speed. Nice easy one. It's just recollection. KE is 1/2 mv squared. Don't forget it's just the v squared, not anything else. 1 mark. Part 2. So simple calculation. Calculate the kinetic energy of the tennis ball at position C. So at position C, it's just left the hand. It's moving at 5.0 meters per second. It's just plugging numbers into the equation. So kinetic energy is 1/2 times the mass, 0.058 times the velocity, which at position C will be 5.0. We're in standard units, meters per second and kilograms, so we're absolutely fine with that. Don't forget to square the 5, it's v squared. Plug in the numbers and we get an answer of 0.725. Now, what we really should do is look at the significant figures. There's only 2 quoted in the information given in the question. So really I should be rounding this up to 0.73. Don't forget units, this is kinetic energy, so we are in joules. And that is your next 2 marks. Part 3. At position A, the tennis ball is at maximum height. What is the gravitational potential energy of the tennis ball at position A? Ignoring the effects of air resistance. So at position A over here, the KE has been transferred to mgh, i.e. all the kinetic energy has. Okay, right, so question 2. Let's have a look. We have 9 wind farms arranged in a kind of square, and we've got our wind direction coming in from here, and we're told that there's 500 meters between each wind farm. Now read the question, please. Wind turbines in the farm must have a minimum distance of 500 meters between them for maximum efficiency. So they're giving you that information right from the start. Make sure you use it. First question. Suggest one way in which the layout of the wind farm ensures maximum efficiency when the wind direction changes. Well, if the wind direction does change, say if it comes from over here, because of this layout, you're always going to get a minimum distance of 500 meters. And crucially, it's in all directions. So you need to state that really to get the mark. Again, using the information from the question, maximum efficiency needs to be 500 meters from any direction. It could come from over here, down here. You're always going to get that distance, so they're always going to be working at maximum efficiency. Question 2. The average mass of air passing through the blades of one wind turbine is 51,000 kilograms per second. The density of air is 1.2 kilograms per meter cubed. Write down the equation that links density, mass and volume. So nice and easy. Just recollection. Density equals mass over volume. Pretty sure you can have it in symbols as well. So rho equals m over v. Absolutely fine. Make sure that's really should be a capital V, because lowercase v means velocity. Part 3. Calculate the volume of air passing through the blades of one wind turbine per second. So don't worry about the per second thing, because we're told that we get 51,000 kilograms per second, so it's just plugging numbers straight back into this equation. We want the volume though, so we want this term here, so we're going to have to rearrange. So don't forget, with an equation like this, we can simply swap the volume and the other quantity over here, and you can just go ahead and do that. So volume would now equal mass divided by density. Plug our numbers in. That's going to be 51,000 divided by 1.2. Are we in standard units? Well, 51,000 kilograms, so that's fine, and 1.2 kilograms per metre cubed, so that's fine. So we can do the calculation straight away, and that should give us 42,500. Don't forget units, metre cubed. However, it does also say give your answer to two significant figures. So if you wrote this, you would lose a mark. Really, we should be writing 43,000, should be rounding it up. That's a very easy way to lose marks, and you really shouldn't be doing. Okay, so splitting all this out, let's move on to the next part. So the average power output from one of the wind turbines is 1.6 times 10 to the power 6 watts. So 1.6 megawatts, not particularly impressive. That's for a wind turbine. A nuclear power station can give 2.4 times 10 raised to the power 9 watts, significantly better. And we're told to calculate the number of wind turbines needed to generate power equal to one nuclear power station. So this is easy. All I'm really doing is trying to find out how many times this number goes into that number. So all I need to do is take 2.4 times 10 to the power 9 and divide it by 1.6 times 10 to the power 6. You can do things with the indices here, but if you just want to put it in your calculator, that's absolutely fine. And that will give you 1,500. No units, because this is just a number of wind turbines. 2 marks, nice and easy. Part 5. The UK requires a minimum electrical power of 2.5 times 10 to the power 10 watts at any time. So let's just write that down. 2.5 times 10 to the power 10 watts. Give 2 reasons why wind turbines alone are unlikely to be used to meet this requirement. Well, first reason, it's unreliable. Now, I don't mean it's unreliable in the sense that it's going to break down. It's unreliable because it's not always windy, so we can't rely on it in that sort of sense. Second reason, if you look at this number, this one over here, this compared to this number is quite small. It's 1,000 times smaller, so you would need a large number of wind turbines, an unreasonably large number. 2 marks, and that is question 2. Nice and easy. Okay, so question 3. The specific heat capacity of aluminium can be determined by experiment. Draw a labelled diagram showing how the apparatus used to determine the specific heat capacity of aluminium should be arranged. There's a couple of ways you can do this, so I'll try and show you the differences between the two. First of all, we need to sort of work out what we're actually measuring. So the equation is mc theta, delta theta really, it's a change in temperature. You are given this one, but it's worth learning anyway. So the things we need to measure, if I want to work out C of course would be E over m theta. I need to measure the energy, I need to measure the mass, and I need to measure the temperature change. So I need to set up an experiment that can measure all of these 3 things. So the standard way of doing it is to take a block, you have to excuse my drawing, and we're going to put a heater in it, which is going to be connected to The first way would be to use a joule meter, which is quite easy, but you might not have seen one of these before. And that simply measures the energy transferred, and then obviously to a power supply. You don't need the specific voltages and stuff like that. You just need to know that we're giving it some power there, and that will measure the energy going in. We have also need to measure the temperature change, so we will need a thermometer. So that's great. We've now got the energy from the joule meter, and we've got the temperature change from the thermometer. Separately somewhere you will need a balance to measure the mass. So that's the first way you can do it. If you don't have a joule meter, you can do it another way. Just make that a bit smaller. So connected to the power supply still, I can put a voltmeter across here, and I could also put a ammeter across there, and then I could use energy equals power times time. Electrical power is of course current times voltage, so that could be IV times time, and in this case I would need a stopwatch to measure the time taken for the energy to increase, although I do think the mark scheme kind of ignores that. So whichever one you want, current meter and a voltmeter, or a joule meter, that will be absolutely fine. Okay, part 2. Get rid of all this. So describe how you could use the apparatus you drew to determine the specific heat capacity of aluminium. It's a standard 6 marker. I'm not going to write out a full essay. I'm just going to give you some of the marking points that you need to make. So we need to measure the energy transferred. So whenever you're doing these experiment questions, always state what it is you're measuring and what instrument you're using to measure it with. So measure energy using a joule meter. You could use the ammeter and the voltmeter and the stopwatch, but we'll just stick with this one for now. We're going to measure the mass and using a balance. And that might be obvious, but you know there's a mark there, so make sure you do state it. Other marking points, other things we're measuring, is the temperature with a thermometer. Then we need to say what we're actually doing with these measurements, because it's no good just measuring them and hoping the heat capacity to come out of nowhere. So I would quote the equation mc theta, and I would also rearrange this as well to show how we can actually calculate it. So divide by m theta on both sides, and heat capacity can be given by energy divided by mass. Energy divided by mass times the temperature change. Now that will get you maybe 3 marks or so, and there's more things that we could mention. So with any practical, there's things we can do. We could take repeats, always a good idea, always going to improve our experiment, improve the accuracy. We could plot a graph. Now this will be quite a hard one to do. You want to plot a graph of the two things which are going to change. So I want to plot a graph of temperature against time, maybe, and then work out the gradient and multiply that by mass. You don't need to go into that much detail. We also need to mention safety. Again, it may be obvious, but there are marks for this, so avoid touching the heater for obvious reasons. It might burn you. Okay, let's move on to part 3. Question 3, part 3. Methods used to determine the heat capacity may give a value greater than the actual value. Explain why. So let's go back to the equation. E equals, sorry, do that again. Let's put it out actually. C equals E over M theta. This is quite a difficult one because it specifically says why give a value greater than the actual value. Well, the problem is actually your measurement of the temperature. Your measurement of the mass is going to be fine, your measurement of the energy is going to be fine if you're using a joule meter, but your temperature is not. And that's because some of the energy will go to the surroundings. So that's kind of not what we assumed. We of course assumed that all of the energy here has been transferred into increasing the temperature of the metal block, but in actual fact some of the energy will have gone somewhere else. So that means that this one here, this temperature change, will be smaller than what it should be, because not all the energy is actually going into heating the block up. Now of course if I divide by a smaller number, it will give a larger value for heat capacity, because dividing by a smaller number means that this number here is going to be bigger than expected. And of course you can counteract that by making sure it's well insulated, or make sure the temperature change is small so there's not a big difference between the temperature of the block and the surroundings, but there's only so much that you can do. You will find that the values do tend to come out slightly larger than what they should be. And that's question 3. Right, so on to question 4. We have a typical equation for nuclear fission, which I've written out there. And we've been asked to describe the process of nuclear fission, which is actually fairly simple, but there are a few key words that we need to state. So first of all, what's going on in this bit? Basically a uranium nucleus, and make sure you say nucleus, you can't say atom. They will take marks off you for that. Absorbs, we call them thermal neutrons, which basically means slow moving neutron. I don't think you need to say that for this question, but you never know, you might do for your real thing. So I will get to learn that. If the neutron's moving too quickly, it just passes through the nucleus and no fission occurs. Okay, then the uranium-236, which is this one here, splits, and it does this straight away. It's very unstable, it can't really sit around for very long, so it splits into two, what we call them daughter nuclei. You can just say smaller though, 2 smaller nuclei, and also releases some energy in the process, and in this case 3 neutrons. It's not always 3 neutrons, it depends on what these daughter products over here actually equal. So in general you could say 2 or 3 neutrons. The energy is actually carried away by the neutrons. They come out very, very quickly. They have a lot of kinetic energy, so that's the energy that's released by a nuclear reactor, and we can extract that energy, we can slow them down via a moderator and use it to generate steam and electricity and so on and so forth. Okay, right, I'll leave that up there. Let's turn over to see what the next question is. So explain what happens in the process of nuclear fusion. So this is somewhat different. We don't need to go into the details, but essentially light nuclei, something like hydrogen, join to form a heavier nucleus. Now the actual process is a bit more in depth than that, but fundamentally, and certainly at GCSE, that's all we know. The nucleus that it forms is typically helium. Again, we want to talk about nucleus, not atom, so you can lose marks very easily by writing atom. And in that process, actually releases energy. the way it does this is there's a slight mass defect. So if I could weigh the lighter elements here and compare them to the weight of the heavier nucleus here, there'd be a slight mass difference. This would actually be lighter than the first one, and that mass is converted into pure energy. But all we need to write is it releases energy. Right, moving on to question 4, part 3. Okay, so 4, part 3. So we're given some information here. You should have this paper in front of you, so I won't copy it all down. So that's clean. Fission reactors are used in nuclear power stations. Engineers are developing fusion reactors for use in power stations. Fusion uses isotopes of hydrogen called deuterium and tritium. Now they're still hydrogen, they just have extra neutrons on. Deuterium has 1 neutron, tritium has 2 neutrons on, so different isotopes. Deuterium is naturally occurring and can be easily extracted from seawater. Tritium can be produced from lithium. Lithium is also found in seawater and in the Earth's crust. And we'll give you some data here. We're told that fusion releases 3.4 times 10 to the power 14 joules of energy per kilogram. So that's joules per kilogram, whereas fission is not so good. That's only releasing 8.8 times 10 to the power 13, so that's slightly less than 14, again, joules per kilogram. The question wants us to say 2 advantages of the fuel used in the fusion reactor compared with the fuel used in a fission reactor. Right, with questions like this, don't try and invent stuff. You know, the information's given to you there, it's right in front of you. Use that information. It's there for a reason. So the first thing I want to say is releases more energy per kilogram. That's his fusion fuel, obviously. 1 mark, nice and easy. Next advantage, well, we're told in the question it's naturally occurring and can be extracted from seawater. So it's easy to obtain. There are, of course, other advantages of fusion. It doesn't produce much in the way of radioactive waste. It's a very safe sort of process if you can get it to work. But I'm not going to mention them because we really should be using the information in the question to guarantee those 2 marks. And that is question 4 done. Right, so question 5, an electricity one. But don't be scared, it's not too hard. First part, what quantity does the ammeter measure? Again, factual knowledge. An ammeter measures current, not voltage or anything else like that. It should be quite obvious. Part 2, the current in the circuit is 3.5 milliamps. So watch out for that. A lot of people forgot that there's a prefix there. So you need to be in standard units. When the potential difference across the thermistor is 4.2 volts. So I always like to write these things down the circuit. So I've got 4.2 volts there, 3.5 milliamps there, so just to help me. And I want to work out the resistance of a thermistor, which is this circuit symbol here. You need to learn all the circuit symbols. Again, just read them, memorise them, do whatever you need to. So that's equals I, and 4.2 volts is V. We're going to use Ohm's law. I can pretty much guarantee you now this equation will be in your exam at some point in one form or the other because it's so important, and you can solve anything with Ohm's law. We're going to rearrange this because we want to work out R, so divide by I on both sides gives me R equals V over I. Plug my numbers in. 4.2, that's in standard units, so that is okay. 3.5 is milliamps, so I need to do 3.5 times 10 raised to the power minus 3. Or you could write that out as 0.0035. If you don't do that, you will lose a mark. You'll get a reasonable number, but it won't be correct. So plug those in, and R should come out as 12,000 ohms, which is completely normal, or 1.2 kiloohms. Generally, in electronics, if you work in milliamps, then your resistance comes out in kiloohms. It's quite normal to have a very small value for current and quite a large value for resistance. Right, next one, part 3. Calculate the charge that flows in the thermistor in 5 minutes when the current is 3.5 milliamps. So again, standard equation, a required one, Q equals IT. And that comes from our definition of current, where current is the rate of flow of charge. So Q is charge, the rate of flow divided by T defines our current, which is where this comes from. So I want to work out Q. A couple of things that you might get wrong in this one. First of all, again, don't forget it's 3.5 times 10 to the power minus 3 because we're working in milliamps. The next thing is it says 5 minutes. Well, minutes aren't standard units, so we're going to have to convert that into seconds. So there are 300 seconds in a minute, last time I checked. Do the calculation and that comes out as 1.05. Don't forget your units, even though they're given in the exam, I'll write them there. 1.05 C, coulombs. Right, let's get rid of this. And the next bit, part 4. Explain why the potential difference across the thermistor changes as the temperature in the house decreases. So what's going to happen is temperature is going to drop, and that's going to change the resistance of this thermistor here. Thermistors are odd things. When they heat up, they actually drop their resistance, and when they cool down, they increase their resistance. You don't need to know the reasons why, but when it gets hotter, it essentially releases electrons, which means there's more charge carriers, so greater current can flow. But we're talking about when it gets colder, so the resistance is going to drop. The resistance is going to increase. Now, if I get a bigger resistance for the thermistor, this one, then I'm going to get a bigger voltage dropped across it, and I would actually get a smaller voltage dropped across there. Remember, the sum of this one and this one must equal 9 volts, but we can have any sort of combination. I could have 1 and 8, I could have 4 and 5, whatever you want. So as the resistance decreases, gets smaller, which it will do because it's getting colder, the voltage across a thermistor will increase. This doesn't sound right, but that is right. For an ohmic conductor, it would be the other way around. Their resistance would increase as they got hotter, but we're using a thermistor here. Part 5. Circuit shown can be modified to turn lights on and off by replacing the thermistor with a light-dependent resistor. Draw the circuit symbol for a light-dependent resistor. Well, you either know it or you don't, so make sure you know it. Simple resistor with 2 arrows going across it, and that's it. 1 mark. And that's it for question 5. Right, so question 6. In the early 20th century, scientists developed an alpha particle scattering experiment using gold foil. It was Rutherford who did this, and he revolutionised the ideas of what an atom actually looks like. And we've got a simple setup here. We've got some alpha particles coming in from this direction, being fired at a gold nucleus. And the question is asking us, explain how the paths of the alpha particles were used to develop the nuclear model of the atom. So we can't zoom in with a microscope and see these things, they're way too small, but we can see the effects of firing particles at nucleus and make some conclusions from that. So the first conclusion you can make is most alpha particles actually pass straight through. And they're not really scattered by very big angles. So what does that tell us? Well, if they're passing straight through, like this fella for example, then it must be mostly empty space. Because if this was much bigger, you get a lot more particles being deflected. Very few of the alpha particles were actually backscattered or deflected through a large angle. So few of them, 1 in 8,000 I think, were backscattered. And that simply means they came back in the opposite direction. Now, what does that tell us? Well, alpha particles have a charge of +2. They're 2 neutrons, 2 protons. And they know that they're bouncing back. We know that like charges must repel. So that means that the nucleus must be positively charged, because if it was negatively charged, they would not bounce back, they would just deflect over a different angle. Other conclusions you can make: the fact that they actually bounce back, it must be massive. Now, when I say massive, I don't mean big in terms of volume. I mean it must have a big mass. This thing must have a big mass compared to the mass of the alpha particles. So what we're concluding is that most of the atom is empty space, or the mass of the atom is concentrated in a tiny little ball at the centre of the atom, and that ball must have the same charge as an alpha particle, i.e. it must be positively charged. So write that out in nice English and you should get 4 marks, no problem. Right, next bit. This was an odd one because I'm not even sure if this is on the specification, but we can work it out. Niels Bohr adopted the nuclear model by suggesting electrons orbited the nucleus at specific distances. So the planetary model is we have a nucleus and orbiting electrons which go around at specific distances. Explain how the distance in which an electron orbits the nucleus may be changed. So we can fit 2 electrons into the first shell. Well, if I want to move an electron up like that to the next shell, oops, what have I done? Don't want that. Then I need to give it energy. To raise it from this position over to this position here, it would have to gain energy, and if the electron wanted to fall back, it would release energy, which is how lasers work. So what I would need to do is it would need to absorb some energy, and it's going to do this via electromagnetic radiation. So if it absorbs some EM radiation, it gains enough energy to actually jump to a higher shell momentarily, or a higher energy level. So it absorbs some EM radiation and moves to a higher energy level. And this shell of electrons is at a much higher energy than that electron. And in fact, the electrons will try and move back down. They'll try and fill the shells up as soon as they can. And like I say, that's broadly speaking, how a laser generates light. Okay, so that is question 6. Right, question 7. Quite a tricky one, another electricity question. So we've got a graph here of current against potential difference for a solar cell, run light of, I'm just going to write this down, 450 watts per metre squared is incident on it. First one's easy. Determine the power output of the solar cell when the potential difference is 0.5 volts. So the power equation is P equals IV, current times voltage. Voltage 0.5, I've not drawn it on, but it's about there. Use a ruler, go straight to the top, and we can see what it should be. I think it's 0.91, but there's probably some margin for errors in that. So the power, is simply 0.91, which is the current value, multiplied by the voltage, which we're given 0.5. So that gives us 0.455. Probably best to 2 significant figures, so 0.46. Don't forget your units, although again they're given. Watts, 3 marks. Which is quite good. It's quite a generous loss of marks because it's just multiplying 2 numbers together. Right, question 2. Draw a sketch graph to show how the power output of the solar cell varies with potential difference between 0.1 volts and 0.5 volts. you don't need to include values on the y-axis. They have included values on the x-axis, so they've got 0.1, 0.2, 0.3, 0.4 and 0.5. So as we increase the potential difference, the current is remaining constant, but the potential difference is getting bigger. So according to this equation, if I keep a constant current, certainly up to 0.5 volts, then basically what we're saying is power is proportional to voltage in this case. And it will be directly proportional as well. If there's no current there, there's going to be no power. The tricky thing with this is the origin is not where it normally is, because that's 0.1. So actually your straight line graph is going to have some kind of y-intercept. Not really got the scale right on that, but it should be a straight line. It should intercept here, because if you would extrapolate it, that would get to 0. So you could lose a mark if you're not paying attention on that one. Do be careful. Part 3. This is, actually get some room, I'll just delete all this. Part 3, quite a tricky question, to do with efficiency. So the maximum power output of this cell is 0.52. So power is 0.52 watts. The light intensity of 450 watts per meter squared. The cell has an efficiency of 0.15 at the maximum power output. Calculate the area of the solar cell. So the first thing I'm going to want to do is work out what the total power is. So efficiency is useful over total. So I can rearrange this. If I want to work out the total power output, then that's going to be my efficiency divided by, no, sorry, made a mistake. That's going to be my useful divided by my efficiency. If you're working with efficiencies, make sure you don't use a percentage. Make sure you use a number between 1 and 0, otherwise your calculations won't work. So that's going to give me 0.52, because that's my useful power, which was quoted here. That's what the output power is, divided by my efficiency, which is 0.15. It's not a percentage, so that's absolutely fine. And that gives me a total power of 3.47 watts. Okay, so what do we do with that? Well, I want to work out the area. So the area is simply our total power divided by this number up here, which is what we're told that it's working out. The light intensity is 450 watts per meter squared. So dividing your 3.47 by your 450 gives us an area, and it's quite a small one, but that's okay, of 7.7 times 10 to the power minus 3. Don't forget your units. So this bit is probably the tricky bit, but another way to look at it is to say 450 watts per meter squared equals 3.47, which is our total power, divided by the area, which is what you should be starting out. And that should be obvious, because we've got our total power there, which is our watts, and our area there, which is our meter squared. So you can work this out from the units. But it is quite a tricky one. That's certainly getting up to a level 9 type of question. Right, let's just get more on this. Yep, so next bit. A householder has 4 solar cells. Each of the solar cells has a resistance of 0.78 ohms. Explain how the solar cells should be connected so the total resistance is as low as possible. Well, with any circuit, if I wire things in series, so 2 resistances like this, then the total resistance, R total, is simply R1 plus R2. Now that's not what we want, because I'm going to have 4 resistors effectively in this circuit, and I want to get them to be a minimum resistance. However, if I were to wire 2 resistances in parallel, then the resistance drops. Now you don't need to actually calculate or know how to calculate the drop in the resistance. If you're interested, the total resistance is 1 over RT is 1 over R1 plus 1 over R2, where that is R1 and R2. But we don't need to know this equation, that's more of a A-level type of thing. What you do need to know is that arranging resistances in parallel does make them smaller. So your answer, they should be arranged in parallel. And the reason is the current has multiple paths it can take. So it's a bit like opening another lane on a motorway. You'll be able to get more traffic through. Easy 2 marks. That's the end of question 7. Yep. Okay. Right, nearly there. Question 8. So a student investigated the properties of 3 types of insulation. So they've got some insulating material over here and a hot plate which is kept at a constant temperature. So there must be some sort of power supply to that. That's keeping it at this constant temperature. And we have a graph here of 3 different materials looking at the temperature rise. The first question 1, 8 part 1. What was the temperature of the hot metal plate? A lot of people put 20 degrees, which was down here, which is wrong, because they're all trying to reach the hot temperature of the hot plate. Only material A actually gets there, so that must be quite conductive, and then it levels off. So the temperature is in fact 80 degrees, which is this point over here, 80 degrees C. So yeah, a lot of people got that wrong, which is a bit disappointing. Which material is the best insulator? Well, the best insulator would have the worst thermal energy transfer. So material C doesn't reach this temperature. It will do in the end, it will just take a long time. So definitely material C. You need to give a reason, because the temperature was lowest after 10 minutes. That will be fine. Right, part 3. Give myself some space. Another student repeated the investigation but doubled the thickness for all 3 insulating materials. Suggests how using thicker insulation would affect the results of the second student's investigation compared with the first student's results. So read the question. Suggest how it would affect the results. So we're just talking about the results here. If it's double the thickness, you'd expect it to be a better insulator. The heat's going to have a harder time travelling through it. But how is that going to actually affect your results? Well, there's 2 things. There's going to be a lower total temperature rise. So these materials wouldn't reach the highest temperature. We need to give a reason, it's a suggest question. So why is that the case? Because the rate of temperature change or temperature increase would be lower. Okay, job done. Next bit, part 8, part 4. Students have used a thermometer, could have used a thermometer instead of temperature probes and a data logger. And we've got a picture here on your paper of a data logger screen and a thermometer. Give 2 advantages of the data logger and temperature probes compared to a thermometer. A lot of people here talk about accuracy and precision and things, and I don't think that people really understand what's meant then by those terms. First of all, accuracy is how close you are to the actual value, and you've no idea if either the data logger or the thermometer is more accurate, so you can't really say just increased accuracy. What I can say is that the data logger has a higher resolution. It's quite difficult to see, well, they're not impossible, but definitely difficult to see the resolution on the thermometer. It's somewhere between 38 and 39, but I can't be too sure exactly where it is. So the data logger definitely gives a higher resolution and easier to read. Digital things are generally much easier to read, so there's less chance for error, less chance for people to misread it. Don't say things like improves accuracy, don't say improves precision. To make something more precise, you would take repeats and you would look at the spread of results of the data that you've got to see if there were much variation. If there wasn't much variation, you could say it's quite precise. Accuracy is a difficult one to get because you don't know what the true value is, and accuracy is simply a measure of how close it is to that value. So again, use the information in the question. Higher resolution, easier to read. Next bit was done quite well actually. It's an easy question. So we've got some tables of data. I won't write them all out here, you've got them in front of you. And we've got thermal conductivity in watts per metre. It's probably meant to be watts per metre squared, but never mind. Of felt wool, mineral wool, polyurethane foam and rock wool. Now this is a measurement of how conductive they are. So which one is going to be the best type of insulation? You want the one with the lowest thermal conductivity. It's not going to conduct much heat away. So polyurethane foam has the lowest one at 0.03. It's not transferring much energy at all, so that would make the best insulator. 2 marks here, so we need to give a reason. So lowest rate of energy transfer. Okay, and that is question 8 done. Right, question 8. A student investigated how the pressure of a gas varied with the volume of the gas. Mass and the temperature of the gas were constant. So I've not drawn it, but there's some apparatus here. We have a syringe and a pressure gauge. What was the resolution of the syringe? What does resolution mean? Well, it's the smallest increment that a measuring instrument can measure. So looking at this, the scale is quite clearly 1 centimetre cubed. A lot of people put 25, that would be the range of this. That's the total difference between the smallest and the largest measurement. Resolution is the smallest difference it can measure. Easy mark. Don't lose marks on that one. The next one we're looking at this graph over here, and we've got pressure against volume. So they've compressed the gas, read the pressure and recorded the volume. And we want to know what conclusion can the student make from the data in figure 11, which is this graph. Okay, I don't think anyone scored full marks on this. First of all, I can see that the shape of the graph is following a downward trend. So the first thing I'm going to say is pressure is inversely proportional to volume. Oh, not again. There we go. As one quantity gets bigger, the other quantity gets smaller. But you need to be saying the words inversely proportional to score the marks. Start getting used to using the technical vocabulary that's required. You will gain higher marks. It's 3 marks though, so we need to do a bit more than that. That's not worth 3 marks. So we need to prove this somehow. So how are you going to prove that this is an inverse relationship? Well, I'll show you how to do that. What you need to do is you can take any 2 points. I'm going to take, let's say, this point here, which is 8, and that point there, which is 200, if you look at your graph. And I can pick another point as well. Let's say something down here where that is 10, and this point at 10, if you read your graph, is 160. To prove an inverse relationship, what you need to do is you multiply these two numbers together and see what they equal. And if you do this at any point along the graph on an inverse relationship, then we should be getting the same number. So I should say 8 times 200 gives me 1600. And then pick another point over here. I'm going to do 10 times 160. And that also equals 1600. And the fact that these two numbers are the same, that proves an inverse relationship. If you don't know how to do that, then you'll have no chance, but hopefully that will give you some clue if this question comes up again. Right, the next bit, part 3, explain why the pressure in the gas increases as the gas is compressed. So this is some of this is new in the new specification. It seems to be taken from the A-level. Let's look at the marking points involved. So as the gas is compressed, the first thing you're going to say is obviously the volume is decreased. Obviously. So if the volume is decreased, let's just go over here and think about a particle in a box. So a particle here is bouncing around in the box, and as it bounces off a wall, it creates pressure. It exerts a force on the wall thanks to Newton's laws, and force divided by a certain area is pressure. So, or pressure, sorry, is force divided by an area. Let's get that the right way round. Now, if I make the box smaller, it's going to bounce across these walls more frequently. So as the volume is decreased, we're going to get more frequent collisions. Not necessarily harder collisions or faster collisions, because the speed of the particle is going to be the same. So we're going to get more frequent collisions with the wall. So each collision exerts a force. And if I'm having more collisions, I'm going to have a greater force because I'm having more collisions per second. And of course, a greater force gives a greater pressure. So just be careful to mention that the particles don't actually increase in their speed. They're not being heated up. They're just colliding with the same force that they were before, but they're doing it more often. There's more collisions per second, so the average force, the total amount of force per second is increased. Therefore, the pressure must be increased. So that would be 1, 2, 3, 4 marks for that one. Again, quite a tricky question, but once you've seen it once or twice, you shouldn't have a problem. And that's it for that one. Wonderful. Right, question 10. So we've got some information here about the percentage of production of electricity in the UK in 2016. Get the information from the question. The UK government signed the Paris Climate Agreement in April 2016. The agreement commits the UK to reduce the amount of carbon dioxide released into the atmosphere. And it asks us to explain which energy resources should be used to meet the UK's commitment to this agreement. So, of course, of these 4 ones, gas, nuclear, coal and wind, only nuclear and wind don't produce carbon dioxide. So, you can start off with nuclear. That will be your first choice. No CO2 is released. Now, make sure you say during operation. So when it's running, there's no CO2 being produced. But, of course, when we're building it, that does produce some stuff. So which one should we use? Why should we use this as well? Well, it has a high energy density. So what that means is that we don't use much fuel. You'd have to ship 3 tons of coal a day into it. You can just put some fuel rods into the reactor and it's going to work. You could say that there's already being built, i.e. it's a proven technology. We know nuclear power works. We know it's reliable, it's going to give us the energy that we need. The other one from here is of course the wind. So again, no CO2 is released, so that's just the same as that one. Other advantages of wind though, there's no fuel cost. We don't pay for the wind, whereas there is with nuclear power. And you can say it's a renewable. Nuclear power is not a renewable source. It does require fuel, so don't say that for nuclear. Right, part 2. Scrub this out. So part 2, on average there is enough wind in the UK each year to supply all of the UK's electricity needs. Explain why the UK may still need power stations that use fuel to generate electricity. So that doesn't seem to make sense on the face of it, because it says that we don't want that. We said that we've got enough energy to supply all the UK's needs, so why do we need other ones? Well, the key word here is on average. There is enough wind in the UK. So sometimes there's not, or sometimes there's too much. So wind power is unreliable. That's the key point. So unable to meet demand. We can't control when we want it to be windy, and during the evenings when everybody gets home and puts the kettle on, then the demand's going to surge, and wind power won't be able to do that alone. There are some solutions to this. You could look at storing the energy, so when it's windy you try and store some of that energy and use it later on, and those technologies are being looked at. Now that was part 2. Question 10, part 3. All European countries signed the Paris Climate Agreement in 2016. In the future, some European countries will only allow electric vehicles, including the UK. I think we're switching to electric in 2040. Suggest how this is likely to affect methods of electricity generation in these countries. Right, so it's the wording of this. You've got to think, we've signed up to this agreement. If we're going to use electric cars, which are going to be plugged into the national grid, then electricity generation is going to need to improve. It's going to get bigger, because we'll need to generate more to power our cars. Generation. Well, so it's going to have to increase. Now, if we've committed to this Paris Climate Agreement, then it's got to be using clean sources, i.e. nuclear. When I say clean, I mean things that don't produce greenhouse gases. So we could use nuclear, wind, or any other renewables. So we could have hydroelectric, solar power, tidal power, geothermal, those sorts of things. To get to the third mark, you need to sort of reference the Paris Climate Agreement, which not many people did. So because of this agreement, we're not allowed to use fossil fuels such as gas and coal over here. We're going to have to use one of these 3 or 4, 5, 6 other things. Right, that's question 10. And last but not least, quite a difficult question on power, certainly towards level 8, level 9 sort of things. We've got a battery powered drone, and the battery in the drone can store 97.5 kilojoules of energy. Watch for the prefix, there's 1,000 there, so it's 97.5 thousand joules of energy. And the power output, we're told, is 65.0 watts, which sounds perfectly reasonable. We want to work out the time for which the drone can hover. Well, let's look at our definition of power. Power is the rate at which energy is transferred. So that's energy divided by the time taken. Once I've got that, I can of course swap these two things around. Nice little trick. So time equals energy divided by power. Now it's a case of just plugging the numbers in. Energy is 97,500 because it's a kilojoule divided by the power. That's in standard units, so that's 65.0. I put the units in. Do the calculation, and that should give you 1500. Remember, time is of course measured in seconds, so we can leave it as that. You don't need to convert it to minutes. That's going to be about 25 minutes, exactly 25 minutes, which sounds perfectly reasonable. Check your answers. You know, if you're getting something which is like 2 minutes or 3 hours, that doesn't sound right to me, so you've probably made a mistake somewhere. Right, the next one, very difficult question. Let's get rid of this. So the battery powers 4 motors, remember that? And each motor has a resistance of 1.60. There's a clue here, 1.60, so I want 3 significant figures in my answer. And the power is 19.6 watts. This is for each motor, not for them in total. So what I'm going to do is we want to work out what the current in the battery is. So your first choice might be to use P equals IV, and that seems fairly reasonable, except that we don't know V, so we can't calculate the power or the current from that. What I'm going to have to do is rearrange this and substitute in Ohm's law. So I want to eliminate V. I know that V equals current times resistance, so I can place this in there, and I get P equals I times R, otherwise known as I squared R. Now I want to calculate I, so I'm going to rearrange this. I squared is P divided by R on both sides, and I want to take the square root of that so that I can eliminate the squared term there. I is going to be the square root of P over R. So plug your numbers in, that gives me root, the power is 19.6 standard units, that's fine, divided by the resistance 1.60, that's fine, it's in standard units, and that gives you 3.5 amps. But that's not the answer, because there are 4 motors, so I need to do 3.5 times 4, remember we have 4 motors, which gives me 14 amps in total. And that is it, so I hope that's been of some help to you. Let me know if you want me to do more of these. And it's about 11 o'clock now, so I'm going to bed. Good night.